Hi everyone, Dr. J here, and in this video we're going to be talking about Gauss's law for gravity fields. Gauss's law, as it says in the book, Gauss's law states that the total mass in a region is proportional to the normal component of gravity attraction integrated over the closed boundary of the region. What do I mean? Okay, so let's draw a picture. So I've got some half sphere right here. So we're talking now in 3 dimensions. Here's the surface or the top of that half sphere. We'll call that the surface. That's SP. And then the bottom kind of bowl part of that surface we'll call SH. There's some excess mass here. We'll call that MT. What do I mean by excess mass? We've got a uniform density, a uniform background density distribution. So everything in the background is uniform. And then we've got some extra mass sitting here. And the idea here is coming from exploration. So the idea is we're taking a bunch of measurements of gravity over the surface of this thing, and we want to know how much extra mass is in this area. So just imagine, let's say you're exploring for a mineral deposit. Those minerals are going to be most likely more dense than rock. So rock density might be 2.67 grams per cubic centimeter. And ore density might be 4 grams per cubic centimeter, or more than that or less, a little bit, depending on what ore that we're talking about. Either way, Gauss's law allows us to say something, and again, I've kind of drawn this weirdly, but this is a 3-dimensional distribution inside of this bowl-shaped thing. So what we're going to do is we're going to use the divergence theorem. Divergence theorem says the integral over a surface. We're going to apply the divergence theorem to the gravity field. So G dot N ds. So we're going to integrate the normal component of the gravity field over the surface. What's the normal component? Right? It's the point exactly perpendicular to the surface all the way around. So that would be the normal component. That's the normal component. Here we're straight up because the top is flat. So that's the normal component. We're integrating the normal component of the gravity field around the whole surface. And this is just divergence theorem. It's going to be equal to the volume integral of the divergence of the gravity field. So volume integral of the divergence of the gravity field is equal to a surface integral of the normal component around the surface. Okay? And in this case, we have to integrate all the way around, right? So not just the top and bottom, right? What is this? This is del dot G. Well, that's also equal to integral over the region of del squared U. That's our gravity potential, right? Because of that relationship that we have, G is equal to grad U. Okay, so there we go. Now, we learned something in the last video about Poisson's equation, or one of the last videos about Poisson's equation. What did we learn? We learned that this is equal to, this is negative 4 pi g density, and just negative 4 pi g times the density. I guess there's a unit vector in there probably. Okay, so we can plug this in. We can just continue on. So this here now, integral of the normal component of the gravity over the surface is going to equal negative 4 pi g, those are all constants, integral of the density over the volume. Well, what is this? If we're talking about our density excess, we're talking about our density excess, right? Remember, we have principle of superposition. So we can subtract out the component of the density, which is the uniform background, and we can just consider, no, we don't need the integral anymore, because we know in this case what that density is. It's MT. There we go. So this is now equal to the gravity normal component over this area. Well, that's interesting. Except there's a problem. How in the world can we measure the gravity field on this bowl thing? We can say if the area is large enough. So if we sort of give this half sphere a radius, call that radius A, and we take the limit as A gets very large, then it doesn't matter where this mass is located or how big it is, it's going to behave like a point mass. And in fact, we can essentially ignore it when we do the integral over this bowl. And so in that case, what we can actually do is here, we're going to change this integral to be the integral over the surface, SP, gz ds. Okay, so again, I'm not going to walk through all the detailed math because you can see it in the book there. But the idea is we make this sphere very, very large, well outside of the area where the mass anomaly is located. And then that integral, this surface integral over this part basically cancels out. We can pull this -2 out, 2 pi times capital G times the total mass, the mass anomaly. What is this? This is just the vertical gravity over the surface of this sphere. So theoretically, what this means is that if we could measure gravity over the surface of this sphere, then we could just integrate that and calculate what is the total mass anomaly of that area. This could be really useful, right? Let's say you're looking for a mine. You want to know how much ore is in that mine. Well, voila. You just take a bunch of measurements of gravity and you can calculate out what the total mass anomaly would be. What's the problem with this? Problem with this is that this doesn't take into account the fact that the surface of the Earth is not flat. There's probably mountains and hills around where you're trying to survey. There's probably lots of different things that are causing mass anomalies, and you might not be able to get a big enough survey to kind of get away from all those anomalies in the area of your ore. You might run into the next mine over, or any number of things, a fault or whatever. So in practicality, this is probably a limited method, but it is in fact a useful method for exploration. And actually, we're going to talk about this in more detail when we talk about different applications of gravity exploration, where we try and separate out effects of a regional field versus effects of a local field. This is a big deal in typical gravity exploration for minerals or oil and gas or whatever. You try and separate out the effects of the regional field, the background density distribution, from our local mass anomaly that we're really interested in, whether that's an ore, whether that's some fluids or whatever it is. We want to isolate that component, and then we could potentially apply this method to estimate that total mass anomaly. So that's Gauss's theorem for gravity potential. I'll just mention, I won't write anything down, but I'll mention the Green's equivalent layer. Green's equivalent layer theorem says that any mass distribution, or the gravity field from any mass distribution, can be replicated by distributing the mass appropriately over some equipotential surface. What does that mean? It means the potential P caused by a three-dimensional density distribution is indistinguishable from a thin layer of mass spread over any of its equipotential surfaces. That's called the Green's equivalent layer. It's a thin layer of mass over an equipotential surface of a 3D field. And those two things are indistinguishable. What it means, it's just the non-uniqueness problem for gravity. So gravity fields are very non-unique. That means that one particular gravity field could be caused by any number of different density distributions inside. That's one reason why this Gauss's theorem thing is so powerful, is because you get the total mass. It doesn't matter what it looks like. It could be distributed in a large area, a small area, in lines, in cubes, in circles, in whatever. It doesn't matter. We're just getting the total mass of that particular anomaly. And in general, we can't get the spatial distribution of gravity or the spatial distribution of density that produced a particular gravity field. We can't get that uniquely. There are many different gravity distributions, and so much so, and that's what the equivalent layer theorem means, so much so that you could even have a 2D distribution of mass over a surface, and that would produce an equivalent gravity field to whatever any given three-dimensional gravity field that you might encounter in the real world. So gravity is uniquely non-unique. That's probably not the greatest phrase to use, but it's very non-unique. There are many different distributions that can fit the data that we observe. And there are various tricks that we can kind of do to try and minimize that non-uniqueness. Maybe we pull in another geophysical method to use. Maybe we make measurements at different heights or different gridding patterns or whatever. So very non-unique. All right, well, that wraps up our chapter on gravity potential, and we will start in on magnetics potential in the next module.